In this video, we solve problem 2.2.13 from the Nagle Fundamentals of Differential Equations text, 7th edition. We're asked to solve this differential equation, and then the problem statement says an implicit solution in the form f of x, y equals c is this function equals blank, or this function equals c. So you have a blank equals c, so you're just going to find that function of x and y. Where c is an arbitrary constant. First of all, we can tell just from the form of this, I've got a function of x times a function of y, that this is a separable differential equation. It's possible for me to get all of the y's on one side and all of the x's on the other, and then solve, anti-differentiate both sides with respect to x and y. So we're going to start the problem by doing that. We notice that it's separable, so we separate the variables. Again, this is because this is a function of y times a function of x. If a differential equation can be written in this form, then we know it's separable. And so we have this now. And I'm leaving a lot of space, so I'm going to multiply and divide as necessary in order to solve this. Okay, so I want a function of y times dy equal to a function of x times dx. So in order to get the dx over here, I'm going to multiply both sides by dx. Now that doesn't exactly cancel these out because that is a function. That's the derivative of y with respect to x times dx. But remember how we define the differential of y. If we have y equals x squared, just for example, dy is defined to be the derivative of this function times dx. Now normally, or typically, we would say if y is equal to f of x, dy is equal to that derivative times dx. But we could just as easily say that that derivative is dy dx. We could use Leibniz notation rather than prime notation. And you might think that these are sort of canceling out, and so we have dy equals dy, but they're not canceling out, but by definition, dy is this derivative times dx. That was the definition of the differential that we discussed in Calculus 1. So this here, it's kind of like the dx's cancel out and we get dy because the derivative times dx is the definition of dy. And I've got a dy on this side, and I've got a function of x times a function of y times dx over here. Now I don't want this function of y on the right-hand side, so I will divide both sides by 2 plus y squared to the 3/2 power. And then these reduce, and what we're left with is a 1 over 1 plus 2y squared to the 3/2 times dy equals 5x squared times dx. Now, if you had a dy over that, that would be fine as well. But I like to write it in this way so that I can see what that integrand is. So after we have separated the variables, all we do is anti-differentiate each side with respect to the variable that is on that side. Now this side is really easy, so I think I'll do that first. The antiderivative of 5 times x to some power is 5 times x to the 1 larger power. We're going to add 1 to the exponent and then divide by the new exponent. And we can divide this by 3, or we could divide the 5 by 3. Then we'll add a constant of integration, c1. But this side is a little bit more challenging. You might ask yourself, do I have a basic rule for that? And we don't. You might be tempted to use u substitution, where u is equal to 2 plus y squared because you've got that function nested inside another function. But the derivative of 2 plus y squared is 2y, and there's not a y up here. So u substitution is not going to work. Integration by parts is also not appropriate. So what I would say is this kind of looks like a y squared plus a constant squared, where that constant squared is 2. So that if this 3/2 wasn't there, that would be an inverse tangent or an arctangent function involving y when we compute the antiderivative. But we have this 3/2 power. Since we have a 3/2 power, and it kind of looks like an arctangent antiderivative, but it's not an arctangent antiderivative, we're going to use trigonometric substitution. With a tangent substitution. So we'll have y equals a times tangent of theta, and we'll be able to write all of this in terms of theta and anti-differentiate from there. Now, if you're my student and you're worried and you're thinking, oh my goodness, I didn't realize I was going to have to use trig sub in this class, know that you're going to have to use it for this one problem, but I would never put a trig sub problem on a quiz or an exam in our differential equations class. In our differential equations class, if you know U substitution, integration by parts, partial fraction decomposition, and algebraic manipulation techniques for writing that integrand in one of the forms that we can use, one of the forms that we know how to anti-differentiate, you'll be good to go. But for this particular problem, we have to use a tangent substitution. So I'm just going to focus on this. And we will evaluate this integral using trig substitution, which is a good exercise. So I'm going to say, let's anti-differentiate the expression on the left-hand side, LHS for left-hand side, using trigonometric substitution. And here we need to identify A. Since the integrand involves a variable squared plus a squared, we're going to make a tangent substitution. So we're going to let y equal a times tangent of theta. Okay, so a squared is 2. A is always the positive square root, so a is the square root of 2. Because our integrand involves y squared plus a constant squared, we're going to let y equal a, which is square root of 2, times tangent of theta. Now, when I teach my Calculus 2 students trigonometric substitution, I call this step preparing to substitute, because the idea is if you have an integrand that looks like this and your basic rules do not apply, and U substitution does not apply, and integration by parts does not apply, we will write the entire integral in terms of theta, anti-differentiate, and then we'll use a triangle in order to back substitute and write the final answer in terms of the original variable, in this case, y. So I'm going to call this step the preparing to substitute step. So we have what y is in terms of theta. Now we need to know what dy is in terms of theta. And it's not just d theta. It's the square root of 2 times the derivative of tangent of theta, which is secant squared theta. Don't forget to multiply by d theta. And we also want to simplify this 2 plus y squared. We want that in terms of theta as well. So you've got a product here. If you're squaring a product, just square each term separately. This is going to give us 2 plus the square root of 2 squared is 2. And then we've got a tangent squared right there. And then if we factor out a 2, we've got 1 plus tangent squared times 2. And we've got a Pythagorean identity that says that 1 plus tangent squared of some angle is secant squared of the same angle. In this case, our angle is theta. So this is 2 times secant squared theta. Okay, so all of this was the prepare to substitute step. And now we're going to substitute. We're going to write everything up here. Every single piece needs to be written in terms of theta instead of being written in terms of y. So I have 1 over 2 plus y squared to the 3/2 times dy. Now 2 plus y squared is the same as 2 secant squared theta, provided that we're making the substitution. So this right here can be replaced by this here. We're literally writing this instead of this. Now dy, again, is not d theta. dy is being replaced by this. Because in terms of theta, that's what dy is. It's the square root of 2 times secant squared theta d theta. So this is what I would typically call in calculus 2 our second step. We're going to substitute, simplify, and antidifferentiate. The whole point of the substitution is to write this integral in a form that we can antidifferentiate. And then once we've done that, we can back substitute. We can write our answer in terms of y. Okay, so now here, remember again, you've got a 2 raised to this power, or a 2 times a secant squared raised to this power, which means that this denominator, just the denominator, not the numerator, is the same as 2 to that power times secant squared of theta to that power. We're just applying this property again, but in this case, the exponent is not 2, the exponent is the 3/2. So I will continue my work on another page. And here's another algebraic aside. If you have x to the 3/2 power, that's the same as x to the first times x to the 1/2, because 1 plus 1/2 is 3/2. So I like to think of that as x times the square root of x. So that's actually what we have here in the denominator. We have 1 over 2 to the 3/2, which is 2 times the square root of 2. And then here you've got a secant squared raised to the 3/2. So the appropriate algebraic property for that is this. If I have something raised to a power, we multiply the exponents. In this case, we're going to multiply that 2 and that 3/2. The 2's will reduce and we'll just have a third power. So this is secant cubed theta. And we're still multiplying by square root of 2 times secant squared theta, d theta. And that's very nice, very convenient. The square roots of 2 reduce. 2 of the secants will reduce with 2 of those, so we're left with 1 in the denominator. So now we have 1 over 2 times the integral of 1 over secant of theta with respect to theta. Now at this point, you might think you don't have a rule for that, but remember from trig, cosine of theta is actually 1 over secant of theta. And we've got a rule for cosine of theta. So we've got one of our reciprocal identities, which tells us that this entire expression is the same as cosine. So we have the antiderivative of cosine of theta with respect to theta, which we all remember is sine of theta plus c. Okay, so that is the antiderivative. We have substituted, simplified, and antidifferentiated. And all that simplification involved a lot of algebra, a lot of exponent properties, a little reciprocal identity, and then finally we were able to antidifferentiate. We got that integrand simplified to a form that we had a rule for, so then we just applied it. But again, theta is just something that we made up. It was something that we made up so that we could evaluate this antiderivative. So we need to go back to y. The answer for this should be a function of y. When I take the derivative of that function of y, I should get 1 over the quantity 2 plus y squared to the 3/2 power. In order to get back to y, what we do is we take the original trigonometric substitution, which is right here, and we use it to label the sides of a right triangle. So this is the third step. We're going to draw and label the sides of a triangle. And I'm using that as a triangle, not a delta sign. Using the initial substitution, y equals square root of 2 times tan theta. So if I take this and I divide both sides by square root of 2, we have tangent of theta equals y divided by square root of 2. And remember from trig, SOHCAHTOA, tangent is opposite over adjacent. So I can draw a triangle like this. If this is my theta, the opposite side would have length y when the adjacent side has length square root of 2. And this squared plus this squared equals the hypotenuse squared. So the hypotenuse is the square root of y squared plus 2. Okay. Now we want our final answer in terms of, or we want our final answer, which is 1/2 sine of theta in terms of y. So now we can use this triangle to find 1/2 sine of theta, or just sine of theta in terms of y. Because we know what the ratios of those sides should be, because we've got these side lengths relating back to that angle theta. So we've got sine of theta here. According to SOHCAHTOA, that's opposite over hypotenuse. The opposite side is y, when the hypotenuse is square root of y squared plus 2. And we want 1/2 of that. That's our answer. And of course, we want to simplify. And then remember the big picture, we were solving a differential equation, not evaluating an integral, even though solving that differential equation involved evaluating an integral. So we have the integral of 1 over 2 plus y squared to the 3/2 power is 1/2 times sine of theta plus c. And sine of theta can be replaced by this. So that's y over the square root of y squared plus 2. And of course, we could write that as a single fraction. Just multiply straight across, and you get that right there. Now, if you're not sure that that actually works, that the derivative of this is actually equal to that, you should check at this point. Actually, I think it's a good idea to check, so let's check. Let's take the derivative with respect to y of this quotient. And given what we're about to do, since we're differentiating, it would be helpful to write that square root as a 1/2 power. It's this power over, or it's this number over this number in the exponent. According to the quotient rule, we get low d high. Bottom function times the derivative of the top function with respect to y, minus high, that's y, d low, derivative of the bottom function. So we'll have 2 times, you have a function raised to the 1/2 power, that's 1/2 times that function raised to the 1 less power, times the derivative of the inside by the chain rule. Derivative of the inside is a 2y. That's low d high minus high d low over low low. Or if this is high and this is low, low d high minus high d low over low low. Or if you prefer more traditionally, if we have a function of y here and a function of y here, we have the bottom function times the derivative of the top function minus the top function times the derivative of the bottom function over the bottom function squared. And that's that mnemonic, low d high minus high d low over low low. And the d is an operator, it operates on what's in front of it, so you're taking the derivative of the top function, the derivative of the bottom function. That's what I have applied here. Mr. Pink, my high school calculus teacher, taught me that. I'll never forget. And let's see what we get when we simplify. Hopefully we get this. I know this is not differential equations, but it's a good review. Okay, so we're here. And now we have 2 times y squared plus 2 to the 1/2 power. And then we have a minus y times 2y, so it's minus 2y times y is y squared, times a y squared plus 2 to the negative 1/2 power. I think I'll put that in the denominator. It's a negative power, puts that expression in the denominator. And then here we've got a product. I'm squaring this and I'm squaring this. 2 squared is 4. And if I take this, which is a square root, because a 1/2 power is a square root, and then I square it, I just get y squared plus 2. Okay. Now, I've got a compound or a complex compound fraction. I don't remember the appropriate term. But I've got a fraction within a fraction, and I'd like to get rid of my fraction within a fraction. So what we'll do is we'll take the numerator and the denominator of this much larger fraction and multiply by the LCD of the denominators within the smaller fractions. Since there's only the one denominator of y squared plus 2 to the 1/2, we're going to multiply the numerator of the larger fraction and the denominator of the larger fraction by that expression. And then don't forget to distribute. This gets multiplied here and here. Every single term gets multiplied by that y squared plus 2 to the 1/2 power. Now I have 2 times y squared plus 2 to the 1/2 times y squared plus 2 to the 1/2. Add the exponents, so that's 2 times y squared plus 2. Here, when you distribute, these guys are just going to reduce. And so you'll have a minus 2y squared. And then down here, you've got 4, and that's a y squared plus 2 to the first times a y squared plus 2 to the 1/2. Add the exponents. And what do we get? Well, if we distribute, we've got 2y squared plus 4 minus 2y squared all over 4 times y squared plus 2 to the 3/2. These guys reduce, the 4's reduce, and we end up with a 1 over y squared plus 2 to the 3/2. Okay, and that's exactly what we're supposed to get. So we evaluated that integral on the left-hand side, and we set that equal to the result of the integral on the right-hand side. And we checked it out. We're sure it actually worked. So we have y over the square root of y squared plus 2 times 2 equals 5 over 3 times x cubed plus c1. Oops, and I am just now realizing that I made a mistake pretty early in the problem. This is a 5x to the 5th, not a 5x squared. Somehow I went from here to here and I wrote it as 5x squared. So that should be a 5th power, which means that should be a 5th power, which means that should be an x to the 6th, and that should be a 6. Sorry about that. If you caught that earlier, good, because that means you're doing it right. So the left-hand side is still correct, but this should be a 6, and this should be a 6. Now, the form of the solution that they want is this. They want some function of x and y equals c. Well, we could take this and subtract the 5/6 x to the 6th from both sides. And that is equal to a constant c. I used c1, but you could use c if you want to. And this is what I would type into the box. Now, due to the nature of this solution, there are lots of different ways you could write this. If you wanted to get rid of the 2, you could multiply the whole equation by 2. And then 2 times c1 could be that c. Or if you wanted to get rid of the fractions entirely, well, you couldn't get rid of, well, you could get rid of this piece if you wanted to. If you wanted to get rid of the fractions entirely, you could multiply the entire equation by 6 times the square root of y squared plus 2, but then the y squared plus square root of y squared plus 2 would end up over here with the c, so we don't want that. But you could get rid of the 6. You could multiply everything by 6, and 6 times c1 could be that c. But all of those are equivalent to each other. This is the form that my lab math wants, so this is what I would type into that box. Let me know if you have any questions, and again, if you're taking my differential equations class, trig substitution will not come up on your quizzes, even though it was required to solve this problem.